Okay, hello everyone. It's a pleasure to be here today to share with you some insights of my research entitled Crowd-Based Illuminance Map, which is an approach to quantify and visualize daylight perception in virtual environments and compare it to quantitative metrics. So a little background first. My name is Mohammed Hegazy, and I am a member of the Architectural Morphology Lab at Osaka University in Japan. And in our lab, we have a wide range of interdisciplinary research topics, ranging from BIM to simulation to anything computational, basically. And for my research, it's basically the intersection of three disciplines, which are mainly daylight performance and user-centered design and virtual reality based on immersive virtual environments, IVE. So as an introduction, we all know that daylighting is not a luxury for human beings. It's a necessity for a livable environment. And so there are numerous studies that have proven that daylighting has tremendous positive effects on our well-being and productivity. And because of this, it is very important to know how to quantify or how to know where is the daylighting is good or not good, which is a very wide expression. So, for example, the quantitative metrics, which are mostly based on building performance simulations, are good, accurate, and necessary for our design phase. But when we compare them to the actual needs of users and indicators like visual comfort, among other aspects, there is kind of a questionable relationship or gap between both of them. They are not completing each other. And because of this gap, it's not surprising that we find studies that prove that green buildings, like LEED buildings and other types of sustainable certified buildings, are not performing better than traditional buildings, but sometimes they are even worse. And to try to bridge this gap, IVE or immersive virtual environments are being used now as a replicate for the real environment. And immersive virtual environments are really advantageous when it comes to mobility, to their interactivity, and being very cheap compared to doing these experiments in real environments. However, from our literature review, we could find a number of limitations to the current studies in this aspect, mainly related to the scale of the projects that are being discussed. Also, the locomotion techniques are lacking in this most of these studies. It's just one point of view where user can only move his head but cannot move inside. Also, it is not interactive enough to offer a proper immersive experience, and also the output is not directly comparable to quantitative metrics, for example, like Illuminance map or annual daylight metrics. And of course, realism is still not convincing enough. And so my main question of research is how we can improve the outputs of daylight perception in IVEs and compare these outputs against quantitative metrics. And to do this, we need to develop a new system, a new virtual reality system that is more interactive, more photorealistic, and also can be customized by users. And we need to add more gamified content or interactive content or challenges to the users inside these systems. And basically, using this approach, we can acquire what we call a crowd-based illuminance map based solely on user perception of daylighting. So to validate this aim, we needed a case study to use the system for. So basically, we selected Kimball Art Museum in Texas as our main case study for this experiment. So we made a full detailed model, a 3D model for the museum from scratch, using the original textures from the building. And then we rendered two types of rendering for this museum to compare real-time rendering in game engines to normal offline renderings in V-Ray. And this is the experiment workflow or protocol for our experiment. And the most important part here is the one in the red frames, where users could change the daytime inside the virtual reality as much as they want. But in our experiment, we limited it to only 2 times, 9 a.m. and 6 p.m. And users could move freely inside the environments. They could switch on and off the artificial lighting. And the most important part here was the tasks that we have given them. It was that they can walk freely inside the environment, and when they find some scene or some area inside the environment that is more interesting or less interesting in terms of daylighting, they should snapshot it using the controllers that they have, and then they rank it into 4 rankings, whether it is very dark, or bright, or very bright. And to illustrate this is a simple demo for one of the users using our system. So as you can see, a user can move freely. And the freezing time that you see, this is when the user is taking a snapshot. And it's a totally free experience, so user can walk and wander as much as he or she wants. And only when he or she finds something interesting in terms of daylighting, they snapshot. And of course, they could use their controllers to change daytime from 9 a.m. to 6 p.m. And instantly, they could see the difference between daylight effects in both daytimes. So we used the snapshots that we collected from all the users to make what we call as a crowd camera map. So the map here shows every snapshot that was snapshotted by users, and it was tagged by position and by the target that the user was looking at. And also it was tagged by being dark or bright. And then we used image processing software to add ambient coloring to the maps that we have collected using the snapshots to acquire this kind of illuminance maps that are basically based on pure perception of users inside VR without any kind of quantitative simulation. And then we tried to compare this subjective map, heat map, to a quantitative metrics like Illuminance map using VELUX Daylight Visualizer. But actually we couldn't, because they are based on very different data sources. So our map is based basically on the feeling of users for the ambient environment. But the Illuminance map was based on the projection of luminance flux on horizontal surfaces. And to solve this problem, we had to develop a new metric, quantitative metric, that is image-based or based on the same data source that we used inside the game engine, the rendering in real time that we have used. So we divided the floor plan of the virtual environment into 162 points, and we took a 360 image for each one of these points, and using the luminosity histogram in Photoshop software, we could acquire what is we call as image-based luminosity mean values, which are a quantitative metrics based on the luminosity of each pixel of the 360 image that we have collected, and thus it is based on the surround environment, not in planar projection. And using the data from the quantitative metrics that we have developed, we could compare both the rankings that we had acquired from users with the mean luminosity values that we have acquired from the quantitative metrics that we have developed. And using the scatter plot, we have found that there is a statistically significant correlation between both metrics. Another interesting finding by our experiment was this violet bars. As you see here, the purple bars. Like, we know that red bars are bright and blue bars are the dark bars, but violet bars are what we call mixed perception, or some of users found it dark and other users found it bright. So, for example, here are 10 scenes. They are exactly, mostly the same scenes that are snapshotted by users, but one user say it's a bright scene and the other user say it's dark. But in fact, they are basically same scene at same time. So it was kind of interesting why users have different perception even in VR. So this is an ongoing project for sure. So we still have some challenges and some limitations to cover. Especially, we are investigating why mixed perception happen, why some users can have different experience from the same scene. Also, how to enhance and improve our system in terms of motion sickness, for example, which is a known problem for VR, and how to compare our metric, our subjective metric, to more quantitative daylight indicators. And through this enhancement, we hope to reach a unified metric that can consider both the quantitative and the qualitative qualities of daylighting in our buildings. Thank you so much.